Welcome back to Explained, where we take these complex tech topics and try to make them make sense.
Yeah.
Today, we're diving into priority queues.
Oh, very cool.
So think of it like
Good
you're
help.
standing in line, but instead of it being first come, first served,
Right.
it's all about who has the most urgent need.
Yeah.
So how do computers manage tasks when some are like, do me now,
Yeah.
and others can just wait their turn?
Right.
Well, that's where our expert comes in.
Yeah, I've dealt with data structures and algorithms.
What's so fascinating is that priority queues aren't just about ordering things.
Right.
They're about strategically organizing things based on their importance.
Exactly.
So it's not just a simple queue.
Yep.
It's a system for figuring out what needs to be handled first.
Uh-huh.
So let's get into the nitty-gritty.
Okay.
What makes a priority queue tick?
So a priority queue is basically like a line where everybody has a numbered ticket.
Okay.
And the lower the number,
Yeah.
the higher the priority.
Makes sense.
And the faster you get to the front.
I think of it like a hospital emergency room.
Oh, okay, yeah.
So a patient with a heart attack is always going to be seen before somebody with a sprained ankle.
Right. Regardless of who got there first.
Exactly.
Okay, so we have this queue, and we can add elements to it with their own priority level.
Yeah.
What else can we do with it?
So we can perform a few key actions.
Okay.
We can add new elements, of course.
Yeah.
But the real power is in how we retrieve the elements.
Okay.
So we can remove the element with the highest priority.
So that's the one that jumps to the front of the line.
Exactly.
Okay.
We can also check if the queue is empty.
Right.
Or we can even take a peek at the highest priority element without actually removing it.
Oh, interesting.
Yeah.
So it's all about managing these priorities and making sure the most urgent items get dealt with first.
Right.
But where do we see this in action?
Well, it's everywhere.
Really?
Priority queues are not theoretical at all.
Okay.
They're working tirelessly behind the scenes in so many systems we use every day.
Like you mentioned, the hospital.
Yeah.
But think about the operating system on your computer.
Right.
It uses a priority queue to decide which tasks get processor time first.
Oh, so it doesn't freeze up when things get busy.
Exactly.
Right.
Or consider network traffic management.
Yeah.
Routers use priority queues to prioritize certain types of data packets.
Interesting. So that ensures smooth streaming for videos and stuff.
Exactly.
Cool.
Yeah.
If you are loving this behind the scenes, look at the digital world. Be sure to follow Explain for more.
Yes, definitely.
Okay, so I'm starting to see how priority queues are really crucial
Yeah.
for keeping everything running smoothly. But how are these queues actually implemented?
Yeah,
It can't just be as simple as keeping a sorted list, right?
that's right. There are some challenges with the simple approaches.
Okay.
Let's say we use a sorted array.
Okay.
Finding the highest priority element would be super fast.
Yeah, because it's always right at the beginning.
Exactly.
Yeah.
But adding a new element would be a pain.
Yeah, because you might have to shift the entire array to maintain that order.
Exactly.
That doesn't sound very efficient.
No, especially if the queue is constantly changing.
What about going the other way?
Yeah.
Using an unsorted array.
Mm-hmm.
Adding elements would be really easy,
Right.
but finding the highest priority would be a huge problem.
You'd have to search the whole array.
Right, which could be super slow.
Yes, especially if the queue is massive.
Yeah, so both of those options have downsides.
Right.
What's the solution?
So the key is a brilliant data structure called a heap.
Okay, a heap.
Yeah, it's kind of a compromise between the order and the chaos of our previous options.
Oh, that sounds intriguing.
Hmm.
What makes it so special for managing priority queues?
So a heap is a complete binary tree that follows a specific rule called the heap property.
Okay, hold on. Complete binary tree.
Yeah.
Heap property.
Yeah.
Can you unpack those for us?
Of course. So let's start with the complete binary tree.
Okay.
Imagine a family tree
Okay.
where everybody has at most 2 children. Yeah.
A complete binary tree is like that, but with the added rule that each level must be completely filled with nodes,
Okay.
except maybe the last level, which is filled from left to right.
So a very organized family gathering.
Exact.
Okay, so we got this nicely structured tree.
Mm-hmm.
What about this heap property?
So that's where the magic happens.
Okay.
The heap property ensures that the tree is always organized in a way that lets us quickly find and manage the most important elements.
Okay.
And there's 2 flavors,
Okay.
max heaps and min heaps.
Okay.
In a max heap, the value of a parent node is always greater than or equal to the values of its children.
So like a tournament bracket where the winner always rises to the top.
Exactly. And in a min heap, it's the reverse.
Okay, the parent is always less than or equal to its children.
Exactly.
So we have this perfectly arranged tree,
Okay.
and the most important element is always sitting at the top.
Precisely.
Okay.
And here's the kicker.
What's that?
We can store this entire heap structure efficiently in an array.
Using simple index calculations to navigate between parents and children.
Wait a second. We can represent a whole tree structure with a simple array?
Yes.
That's wild.
It's a clever trick.
Okay.
So the root of our tree sits at index 0 in the array. Then for any noted index, its left child is at index 2i plus 1, and its right child is at 2i plus 2.
Got it.
And finding a node's parent is just as straightforward.
That's pretty neat.
Yeah.
So we have our heap stored neatly in an array.
Right.
And we always know where that highest priority element is.
Exactly.
But how do we actually work with it?
Yeah.
How do we add or remove elements while keeping this whole structure intact?
So that's where the fun begins.
Okay, let's have some fun.
Adding a new element to a heap is like adding a new member to our family gathering.
Okay.
We first insert the new element at the next available spot in the array, which would be a leaf node in our tree.
Yeah.
And then we do something called heapify up.
Heapify up.
Yes, we compare the new element with its parent. Okay.
And we swap them if needed to maintain that heap property.
Okay.
And this bubbling up continues until the element finds its rightful place.
So adding an element involves a bit of rearranging.
To make sure that heap property is preserved.
What about removing the highest priority element?
So removing the top dog is a little bit more involved.
Okay.
We swap the root with the last element in the array, and then remove the last element, which effectively kicks out the old root.
Right.
Then we perform heapify down.
Heapify down.
On the new root.
Right, right.
We compare it with its children.
Yeah.
And swap it with the larger child in a max heap or the smaller child in a min heap.
Okay.
And this keeps going until the new root settles into its correct spot, restoring that all-important heap property.
So adding and removing elements both involve these heapify operations to keep the heap property intact.
Exactly.
It sounds pretty efficient.
Yeah. It is.
But how efficient are we talking?
So both heapify up and heapify down only involve traveling the height of the tree. And for a heap with n elements, this height is logarithmic to n.
Right.
Which we express as O log n.
In big O notation.
Exactly.
Okay.
This makes heaps incredibly powerful for managing priority queues because adding and removing elements are fast, even for very large queues.
So heaps are a win-win for priority queues.
They are.
But how do we build one in the first place? So in terms of efficiency, merging smaller heaps is the clear winner.
Okay.
Adding elements one by one can lead to a lot of shuffling as elements constantly jockey for position.
Right, like trying to organize a bookshelf by randomly adding books.
Exactly.
Okay.
So building a heap by repeatedly adding elements has a time complexity of O of n log n, where n is the number of elements.
Right.
Merging smaller heaps, however, zips along with a time complexity of O of n.
Wow, so that's much more scalable.
Yes, for massive data sets.
So merging is the way to go when you're dealing with lots of data.
It is.
But are all heaps created equal?
That's a great point.
Are there different types of heaps, or is it one size fits all?
So while the basic heap structure is incredibly versatile, there are specialized heap implementations, each with its own strengths and quirks.
Oh, specialized heaps.
Yes, they're designed to shine in specific situations.
This is where things get exciting.
It is.
Tell me more. Why do we need all these different types of heaps?
Different applications have different performance needs. Some operations might be more critical than others, and certain heap types are optimized to handle those specific operations with lightning speed.
So it's all about choosing the right tool for the job, then?
Exactly.
Can you give me some examples of these specialized heaps?
Absolutely.
And what they're good at?
So we have leftist heaps, skew heaps, binomial queues, Fibonacci heaps.
Wow.
Pairing heaps, and relaxed heaps.
Okay, so we have a lot of heaps.
We do.
Can we just focus on a couple of the most popular ones?
Sure.
And what makes them unique?
So let's zoom in on binomial queues and pairing heaps.
Okay, binomial queues and pairing heaps.
Yes, so binomial queues are known for their efficient merging capabilities.
Okay.
Merging two binomial queues can be done in O log n time.
Right.
Significantly faster than merging binary heaps.
Okay.
So this makes them a great choice when merging priority queues is a common task.
Can you give me an example of when fast merging would be super useful?
Absolutely. So picture merging sorted lists. You could represent each list as a priority queue, and then use a binomial queue to effortlessly merge them into a single sorted list.
That makes a lot of sense.
Yeah. Or think about event scheduling.
Okay.
where you might need to combine schedules from different sources.
Right, that would be a lifesaver.
Exactly.
So binomial queues are the merging champions.
They are.
What about pairing heaps?
So pairing heaps are also masters of merging,
Okay.
achieving it in amortized constant time,
Okay.
or O1 on average.
Right.
This means they can merge heaps incredibly quickly, especially for large numbers of operations.
Oh, wow.
And they also excel at adding elements also with amortized constant time.
So both binomial queues and pairing heaps are great at merging.
Yes.
But pairing heaps are even faster at adding elements.
Right.
Are there situations where you would choose one over the other?
That's a great question.
Yeah?
While both are excellent choices for mergeable heaps,
Okay.
pairing heaps tend to outperform binomial queues in many practical applications. Even though their worst-case complexity for some operations might be theoretically higher,
Right.
they just have less overhead, making them more efficient in real-world scenarios.
So if you're not sure which one to use, pairing heaps might be the safer bet.
Yes.
For our listeners out there, what are some situations where quickly merging priority queues would be essential?
Yeah, that's a good question.
Let us know your thoughts in the comments below.
Yeah, definitely.
So we've covered a lot of ground here, from the basic concept of priority queues to the intricacies of heaps and even specialized implementations. If you're finding this deep dive fascinating, make sure to follow Explained so you don't miss our future episodes on exciting tech concepts.
Definitely.
Before we wrap things up, let's highlight the key takeaways for our listeners.
Okay, sounds good.
Priority queues are a powerful tool for managing items based on their importance.
Right.
And heaps are the engines behind their efficiency. We've explored different types of heaps, their unique strengths, and how they can be used to solve a wide range of problems.
Sure.
But here's a final question for you to ponder.
Okay.
We've talked about priority queues in the context of computers and algorithms.
Right.
But where else do you see the concept of priority playing out in the real world?
Yeah.
It's everywhere, isn't it?
It is.
Share your insights in the comments below.
Yeah, let us know.
That's a thought-provoking question to consider.
It is.
It really highlights how computer science concepts often mirror real-world phenomena. But let's shift gears a bit and dive into another interesting aspect of priority queues.
Okay.
We've talked about adding and removing elements.
Right.
But what about finding a specific element within a heap?
Yeah.
Is that something we could do efficiently?
So finding a specific element in a heap isn't as straightforward as in a sorted array or a balanced search tree.
Okay.
Heaps are designed for efficient priority management, not targeted searches.
I see.
So in the worst-case scenario, you might have to look at every single element in the heap,
Right.
which means a linear time complexity of O of n.
So if you need to search frequently, a heap might not be the best tool for the job.
That's right.
Are there any workarounds or alternative data structures that are better suited for search-intensive tasks?
Absolutely. If searching is a primary concern, you might consider using a data structure like a balanced search tree, which allows for logarithmic time searches O log n.
Right.
You could even maintain a separate index or hash table alongside your heap to track element locations for faster retrieval.
That makes sense. So it's all about picking the right data structure for the task at hand.
Exactly.
But let's stick with heaps for a moment.
Okay.
We've been talking about binary heaps, where each node has at most 2 children.
Right.
Are there heaps where nodes can have more children?
You're thinking of dairy heaps, where each node can have dairyadron?
Dairy heaps.
Yes.
Okay, so a 3-array heap would have each node with up to 3 children. A 4-array heap would have 4, and so on.
Exactly.
Interesting. What's the advantage of having more children per node? Does it change how heaps work?
So increasing the number of children per node can actually make certain operations slightly faster.
Okay, like what?
For example, heapify down the process of restoring the heap property after removing the root becomes faster in a dairy heap because you have fewer levels to traverse.
So more children, shorter tree, faster operations.
Right.
But I imagine there must be some trade-offs.
Exactly. While heapify down might be faster, other operations like heapify up, restoring the heap property after adding an element, can become slightly slower because you have more children to compare at each level.
So it's a balancing act.
It is.
You have to weigh the benefits of faster heapify down against the potential slowdown in other operations.
Right.
Are dairy heaps commonly used in practice?
They're not as common as binary heaps, but they do have their uses.
Like what?
For example, in certain caching systems where you want to quickly evict the least recently used items, A dairy heap with a high number of children can be quite effective.
Fascinating. I'm
Yeah.
starting to see how the choice of heap implementation really depends on the specific needs of an application. But let's shift our focus back to priority queues in general.
Okay.
What are some of the broader implications of using priority queues in software development?
So priority queues are a fundamental tool in software development, playing a crucial role in a wide range of applications.
Okay.
Their ability to efficiently manage and retrieve elements based on priority makes them invaluable for tasks like task scheduling.
Uh-huh.
So operating systems use priority queues to schedule processes, ensuring that high priority tasks get executed first.
Okay.
They're also essential in event-driven systems.
Right.
In systems where events occur asynchronously, priority queues can manage event processing based on their urgency or importance.
I see.
And we can't forget network routing.
Right.
Routers use priority queues to prioritize certain types of network traffic, ensuring that time-sensitive data, like voice or video, gets preferential treatment.
Okay.
Priority queues are also crucial for resource allocation.
Uh-huh.
Systems that manage limited resources like memory or bandwidth can use priority queues to allocate those resources to the most critical tasks.
Wow, so priority queues are truly everywhere, quietly working behind the scenes to make our digital lives run smoothly.
They are.
It's amazing how a seemingly simple concept can have such a profound impact on how we design and build software.
It is.
It's a testament to the power of data structures and algorithms.
Definitely.
By understanding how to organize and manipulate data efficiently, we can create systems that are not only functional, but also elegant and scalable.
Absolutely.
And for all of you budding programmers out there, mastering these fundamental concepts is essential for becoming a skilled and versatile software developer.
It is.
I couldn't agree more. A solid understanding of data structures and algorithms is like having a secret weapon in your coding arsenal. It allows you to tackle complex problems with confidence and create solutions that are both efficient and robust.
Right.
Well said. We've been on quite a journey exploring the world of priority queues, haven't we?
Yeah.
We certainly have. From the fundamental concepts to the clever algorithms that make them tick. It's fascinating to see how priority queues underpin so many essential systems in computer science.
It is.
It really is. And for our listeners who might be new to the world of programming, I hope this deep dive has given you a taste of how powerful data structures and algorithms can be.
Yeah.
They're not just abstract concepts, they're the building blocks of the software that powers our modern world.
Exactly.
And as you continue your programming journey, I encourage you to delve deeper into the world of data structures and algorithms.
Definitely.
There's a whole universe of elegant and efficient solutions waiting to be discovered.
Absolutely.
Well said. But before we say goodbye, I want to leave our listeners with one final thought-provoking question.
Okay.
We've talked about all the technical details of priority queues, but let's take a step back and think about this.
Okay.
How do they play out in your own life?
Yeah.
Think about it. How do you prioritize your tasks, your goals, your time? It's a question worth considering as it highlights the parallels between computer science and our everyday lives.
That's a great point. It's fascinating how these concepts we're exploring have implications far beyond the realm of code.
And that brings us to the end of our deep dive into priority queues.
It does.
We've covered a lot of ground today, from the basics to specialized implementations, and even touched upon some real-world applications.
Yeah.
A huge thank you to our expert for sharing their expertise with us.
It was my pleasure. Always happy to geek out about data structures and algorithms.
And to our amazing listeners, thank you for joining us on Explained.
Yeah.
We hope you found this episode insightful and engaging.
Definitely.
If you did, be sure to follow Explained so you don't miss out on future deep dives into fascinating tech topics.
Yes.
We're always eager to hear from you, so leave your answers to our interactive questions in the comments below.
Definitely.
And if there's a tech concept you'd love for us to explain in a future episode, let us know.
Yeah.
Until next time, keep exploring, stay curious, and keep coding.
Finding a specific element in a heap isn't as straightforward as in a sorted array or a balanced search tree.
Okay.
Heaps are really designed for efficient priority management, not for these targeted searches.
I see.
In a worst-case scenario, you might have to look at every single element in the heap,
Oh, wow.
which means a linear time complexity of O(n).
Right, so if you need to search often, heap might not be the best way to go.
Exactly.
Are there any workarounds, or are there other data structures that would be better suited for those search-intensive situations?
Absolutely. If searching is a primary concern, you might consider using a data structure like a balanced search tree.
Okay.
These trees allow for logarithmic time searches, or log n.
Okay.
You could even maintain a separate index or hash table alongside your heap just to keep track of element locations for faster retrieval.
That makes sense. So it's all about picking the right data structure for the job at hand.
Exactly.
But let's stick with heaps for just a moment.
Okay.
We've been talking about binary heaps, where each node has at most 2 children.
Right.
Or they're heaps where nodes can have more children.
You're thinking of dairy heaps, where each node can have d children.
Dairy heaps.
Yes.
Okay, so a 3-Avery heap would have each node with up to 3 children. A 4-Airy heap would have 4, and so on.
Exactly.
Interesting. What's the advantage of having more children per node? Does it change how heaps work?
Increasing the number of children per node can actually speed up certain operations.
Okay, like what?
For example, heapify down, the process of restoring that heap property after removing the root becomes faster in a dairy heap because you have fewer levels to traverse.
Oh, so more children, a shorter tree, and faster operations.
Right.
But I imagine there must be some trade-offs.
Exactly. While heapify down might be faster, other operations like heapify up, which is restoring the heap property after you add an element, can become a bit slower because you have more children to compare at each level.
So it's a balancing act.
It is.
You have to weigh the benefits of the faster heapify down with the potential slowdown in other operations.
That's right.
Are dairy heaps used often?
They're not as common as binary heaps, but they do have their uses.
Like what?
For example, in certain caching systems where you want to quickly evict the least recently used items, a dairy heap with a high number of children can be pretty effective.
Fascinating. I'm starting to see how the choice of heap implementation really depends on the specific problem you're trying to solve.
Yeah, it does.
But let's zoom out and think about priority queues more generally.
Okay.
What are some of the broader implications of using priority queues in software development?
So priority queues are a really fundamental tool in software development.
Okay.
They play a really crucial role in a whole range of applications.
Like?
Their ability to efficiently manage and retrieve elements based on their priority makes them invaluable for tasks like task scheduling. So, for example, operating systems use priority queues to schedule processes, making sure that those high-priority tasks get executed first.
Okay.
And this keeps your computer running smoothly even when it's juggling multiple tasks.
That's why my computer doesn't freeze up when I have a million tabs open. Are there other examples?
They're also essential in event-driven systems.
Oh, okay.
In systems where events occur asynchronously, like in a real-time game or a chat application, priority queues can manage event processing based on their urgency or importance.
I see.
This ensures that those critical events get handled right away, keeping the system responsive and engaging.
It's amazing to think that something as seemingly simple as a queue can have such a big impact on how we design and interact with software.
It really is.
And we haven't even talked about network routing.
That's right. Routers use priority queues to prioritize certain types of network traffic. This ensures that time-sensitive data like voice or video calls get preferential treatment.
Got it.
This helps maintain smooth and responsive communication, even when networks are congested.
It's like a digital traffic cop, directing the flow of information to ensure the most important data gets through first.
Exactly. And we also can't forget resource allocation. Systems that manage limited resources, like memory or bandwidth, can use priority queues to allocate those resources to the most critical tasks.
So it ensures optimal performance and efficiency.
Correctly.
Wow, priority queues are truly the unsung heroes of the digital world, working tirelessly behind the scenes to keep everything running smoothly. It's a testament to the elegance and power of data structures and algorithms.
Absolutely. By understanding how to organize and manipulate data efficiently, we can create systems that are not only functional, but also scalable and robust.
Well said. If you're enjoying this deep dive into the inner workings of software, be sure to follow Explained for more insightful episodes like this one. And for all you budding programmers out there, mastering these fundamental concepts of data structures and algorithms is essential for becoming a skilled and versatile developer.
Couldn't agree more. A solid understanding of these concepts is like having a secret weapon in your coding arsenal. It allows you to tackle complex problems with confidence and create solutions that are both efficient and elegant.
Couldn't have said it better myself. Before we wrap things up, I'd like to leave our listeners with a final thought-provoking question.
Okay.
We've discussed how priority queues work in computers, but how do they play out in your own life? How do you prioritize your tasks, your goals, your time? It's a question worth considering as it highlights the parallels between computer science concepts and our everyday lives.
That's a great point. It's fascinating how these concepts we're exploring have implications far beyond the realm of code.
And that brings us to the end of our deep dive into priority queues on Explained. We've covered a lot of ground today, the basics, specialized implementations, and even touched upon some real-world applications. A huge thank you to our expert for sharing their expertise with us.
It was my pleasure. Always happy to geek out about data structures and algorithms.
And to our amazing listeners, thank you for joining us. We hope you found this episode insightful and engaging. If you did, be sure to follow Explained so you don't miss out on future deep dives into fascinating tech topics. We're always eager to hear from you, so leave your answers to our interactive questions in the comments below. And if there's a tech concept you'd love for us to explain in a future episode, let us know. Until next time, keep exploring, stay curious, and keep coding.